Chemistry relies on predictability. The stability of a molecule dictates its function, and for over a century, chemists used specific rules to predict behavior. For organic chemistry, the historical baseline of stability is benzene. It serves as the yardstick against which we measure a specific reaction process, electrophilic substitution. This model illustrates that baseline stability. Benzene consists of 6 carbon atoms in a flat hexagon, sharing a cloud of 6 pi electrons distributed evenly across the ring. This symmetry creates equilibrium, resisting chaotic reactions, because the electron density has no weak points. This established a foundational expectation. Any molecule that breaks this symmetrical 6-carbon arrangement should theoretically be less stable and less efficient. Mastering the predictability of benzene represented the ceiling of traditional organic chemistry. Moving past that ceiling required a molecule that entirely broke those established rules. That molecule is ferrocene, a 3-dimensional organometallic compound that defies standard organic intuition. Unlike a purely organic ring, ferrocene features a central metallic iron atom embedded directly into its core structure. The addition of this metal generates a massive kinetic contradiction. When exposed to electrophilic substitution, ferrocene reacts exponentially faster than our benzene baseline. This textbook excerpt details the comparative stability and reactivity of the ferrocene molecule. The crucial data point is in the final sentence. It states that ferrocene's reaction rate is 10 to the power of 6, 1 million times, greater than benzene. This presents a stark contradiction. A million-fold increase in reaction speed usually indicates a molecule is falling apart, yet ferrocene remains structurally intact. To understand how a molecule achieves extreme reactivity without degrading, we have to deconstruct its unique 3-dimensional architecture. Ferrocene belongs to a broader, highly organized class of molecules called metallocenes. The core architectural paradigm of these compounds is the sandwich compound. This structural diagram catalogs these molecules, showing the consistent geometry across different elements. On the far left is ferrocene, defined by the central iron atom. Moving across the grid, the symbols for cobalt, nickel, chromium, and ruthenium occupy the exact same structural pocket. The defining trait of this class is 2 parallel equidistant organic rings, acting as rigid boundaries for the metal atom. Swapping the central metal atom alters the molecule's overarching properties, but this core sandwich geometry remains constant. The organic rings in these diagrams are a cyclopentadienyl, or CP rings. Unlike the 6-carbon benzene baseline, these are 5-membered rings. They lack the 6-carbon entirely. This precise arrangement, 2 5-carbon rings perfectly bracketing a transition metal, is the physical engine enabling the unique behavior of the metallocene family. These molecular sandwiches do not occur naturally. They must be forced together through specific chemical pathways. These equations show the exact steps required to build the ferrocene structure. Equation 2 shows 2 moles of a sodium salt reacting with a metal halide to yield the ferrocene product. The metal halide, iron 2 chloride, provides the foundational iron core. The sodium salt delivers the highly reactive 5-membered CP rings. During synthesis, the 2 CP rings attack the iron atom simultaneously from opposite sides, trapping the metal in the center. Synthesizing a sandwich compound is essentially trapping a heavy metal atom inside a highly charged carbon vise. To analyze why this carbon vise is so reactive, we have to look at the quantum behavior of the electrons trapped inside those 5-carbon boundaries. This heat map compares the electron distribution of benzene directly against the CP ring. In benzene, 6 pi electrons distribute across 6 carbons, creating a diffuse, stable charge. In the CP ring, those exact same electrons are forced into a smaller 5-carbon space. This physical compression forces a significantly higher, denser negative charge concentration than benzene could ever achieve. This density enables 8-5 coordination. The central iron atom doesn't bind to a single carbon. It binds equally to the entire dense pi cloud of all 5 carbons simultaneously. Because the iron atom is fully occupied managing the inner faces of both rings, the massive electron density on the outer faces is left exposed to chemical attack. This explains the million-fold multiplier. The ultra-dense, exposed external electron cloud drives the reaction speed, while the interior 8-5 iron core acts as an unbreakable structural anchor. This three-dimensional architecture creates highly tunable redox properties. The source text concludes by listing 5 documented applications of these sandwich compounds. Application 2 identifies ferrocene's use in blood glucose biosensors. Ferrocene's predictable electron transfer makes it a microscopic relay, translating biological glucose levels into electronic signals in medical devices. Application 4 references manganese sandwich compounds used as anti-knock agents in fuel engines. The stability of the metallic core prevents the compound from detonating prematurely under the heat and pressure of an engine block. Application 5 notes that swapping iron for zirconium or hafnium turns the sandwich into an efficient polymerization catalyst for manufacturing plastics. Endocrinology, automotive engineering, and plastics manufacturing all rely on this exact structural paradigm. By carefully tuning the metallic core within those parallel carbon boundaries, chemists can dictate the resulting macroscopic behaviors. Transitioning from flat 2D organic rings to these 3D sandwiches provided a physical mechanism to concentrate and shield charge simultaneously, enabling the specific chemical behaviors utilized in modern diagnostics, fuel systems, and polymer production.